Hi, welcome. You're just going to wait for a minute and we will get started. Okay, first of all, welcome. Welcome. This is a study session at Vision Village. We are just going to get started right now. And I will present myself first of all. My name is Jessica Stefanetti. I'm a chemistry teacher with over 17 years of experience teaching IB Chem. I'm also an IB examiner, a content creator at Revision Village. And well, this study session has been designed so as to support students through their RV journey. So it has been designed for you, and the whole aim is to get you trained for IB exams. So welcome again. You will see on the chat, there will be soon a link there pasted with a copy of my notes. We will be sharing information here, and you will find a copy of my notes there. So the whole thing is you can just use it and you can just follow the whole session from there. Keep in mind, we will be covering covalent structures and the bonding triangle today, as you can just see here. And I will encourage you, all of you, to use the question and answer section in case you have any question, okay? Keep in mind, you have the chat, there you have the link with all the information, but use the question and answer section just in case you have any question. We will go over the questions at different moments of this study session. The whole purpose is to help you here. And well, we will explore and we will reinforce some ideas related with covalent bonding. The agenda today will be this one. We'll be covering covalent structures and the bonding triangle. So let's get started. Okay, first of all, we should have in mind that the covalent model is just one of the models we have. And there are different ways to describe the nature of the bonding. We will have covalent structures, metallic structures, and ionic structures. We will be focused today on covalent ones, but keep in mind that it's just one type. We also have the metallic structures and the ionic ones. The nature of the bonding is just different. We will do our best today so as to clarify the nature of covalent structures. We should keep in mind that in covalent structures, we do have attractions that are produced between the cations we have in the structures and the electrons that are being shared. The main nature of covalent bonding is that electrons are just shared. Now, in metallic structures, as you probably know, electrons are just free and delocalized throughout the whole structure. And in ionic structures, we just have structures where positive ions and negative ions are just together with the whole structure is held by a strong attraction between those. So as you can see, the nature of the bonding is just different. Keep in mind, again, that in covalent bonding, electrons will be shared. The electronegativity will be a huge concept for us because the electronegativity is a measure of the ability of an atom to attract a bonding pair of electrons. And this concept will enable us to identify covalent structures. The electronegativity difference is very helpful we can see the representation here. And usually we'll see that structures with a high difference in the electronegativity will present ionic structures. But if we have a low difference in terms of the electronegativity, usually those structures do tend to share electrons, meaning they have covalent structures. This is something general. Keep in mind that the whole detail we have here, we can see just here 2 examples, lithium fluoride and hydrogen bromide. These are just 2 examples, but sometimes the electronegativity difference might not be enough. We'll see later on, there are some other aspects so as to take into account. Anyway, might not be enough, but it's very helpful. So from now on, we will keep in mind that covalent bonds will predominate if we have high electronegativities in the atoms that are involved. Usually that would correspond to non-metals. It's not a must, as I told you before. This is kind of a general rule, and we will go into details as we move forward. Lewis structures are just going to be very important for us. What you can just see here is that we have a representation. I don't really know if all of you can see it there, but that's a representation of the carbonate ion. Now, Lewis structures are very important because they allow us to see how electrons are shared. Valence electrons will be always arranged either for a molecule or an ion. We will see how valence electrons will be arranged, and we will use electrons so as to organize the structure there. Electron pairs will include bonding and non-bonding electron pairs. Atoms will tend to follow the octet rule. You have probably heard about it. All of them tend to gain 8 electrons around. There are some exceptions. I mean, some others might be stable with 2, such as hydrogen, and some others might be what we call electron deficient, but many will follow the octet rule. As I mentioned before, in terms of the exceptions, you should remember, it's a good idea to remember that boron and beryllium are 2 exceptions that tend to be electron deficient, meaning they have less than 8 electrons around. Beryllium can be stable with 4 electrons around, and boron can be stable with 6. And then we will see some cases where there are something known as expanded octets, meaning that some elements can just reach more than 8 electrons around. Anyway, I just want you to see that this kind of representation will be huge in terms of being a key idea just to develop all the theory we will see today. Lewis structures should be built, and building Lewis structures is very important. We should follow some steps, and as everything will rely on the Lewis structure build-up, we will see these steps step by step so that all of you can understand how to do it properly. First of all, we should always deduce the overall number of electrons we have, either in a molecule or in an ion. We should consider everything we have. So we have to add all the electrons, and if we have an ion, the charge should be taken into account. Keep in mind that positive ions do have less electrons and negative ions do have additional electrons. We need to arrange the atoms so that there will be always a central one, and then all the other ones will be around. Usually the one that is not repeated will be the central atom in the whole structure. We need to state bonding pairs of electrons between the central atom and the ones that are around. We will call those ones the peripheral atoms, and then we will assign bonding pairs, non-bonding pairs to the peripheral ones so that they can just reach the octet rule. Once we are doing that, then we will check that if there are remaining electron pairs, we will assign them to the central atom. And so we will check if they follow the octet rule or not. If it's not followed by all of them, we might have to reassign electrons. But well, the thing is, you need to do this step by step. So again, keep in mind that if an ion is given, we should count carefully the number of electrons in that structure. Just to practice, we will see the carbonate ion. Here we have 1 carbon, we have 3 oxygens, and the carbonate itself has 2 negative charges. So as you can see, the overall number of electrons here will be 24. Let's follow the steps I just explained just to see how to develop the structure here. First of all, we will state carbon as the central atom and the oxygens around, and we will just state one bond between the central atom and each peripheral. Once we are doing so, we are just going to put the non-bonding electrons around the oxygen so that all of them can achieve the octet rule. If you just check this structure, we already have 24 electrons, meaning we have already arranged the electron. There's an issue here. Carbon is not following the octet rule. Check out that carbon has only 6 electrons around. So the usual thing is that if we have something like this, we just need to take from any of those oxygens, we just need to take a pair of electrons and we just need to put those pair, that pair as a bonding pair. By doing so, we can easily modify this and make carbon stable with 8 electrons around. So that's the next step. We just rearrange the electrons, as you can see here, and the carbon gets stable. We should never forget that we're representing Lewis structures if we have an ion. The ion must be represented between brackets and with a charge on top. So that would be the structure for the carbonate ion. Let's just keep in mind that bonds can also be represented as lines. So you might see this kind of representation either in exams or just books. Sometimes lines are used. It's just something that is fine. So in general terms, we will talk about it like that. Now, multiple bonds might exist. We have just seen that in carbonate, one of those bonds was actually a double bond. Now, keep in mind that multiple bonds are sometimes referred as bond order. The presence of multiple bonds is something usual, and we should have that in mind. When we have a single bond, we will make reference to order 1. And when we have a double bond, we will make reference to that bond being order 2. The same with a triple bond. We will make reference to that one as order 3. So the thing is, the bond order is important because it's not the same to have a single, double, or triple bonds. Here you can just see that the length and the strength of that bond is not the same. The greater the number of bonds we have, the greater the strength of that bond. You can just check here that the bond enthalpy tends to increase as we go down, because the greater the number of bonds we have there, the greater the strength of that bond. This is one thing we should have in mind. But at the same time, as the bond is getting stronger, we should have in mind that those bonded nucleus tend to be closer to one another, meaning that the length also tends to be reduced. I can see that many students are asking are requesting to get some captions of the webinar. I will decline those requirements. Keep in mind, you have already a link on the chat so as to access all the information I'm just sharing here with you. You have it all there. So keep in mind, you can just go to that link and download everything. You can just view the whole presentation there. So don't be worried about getting pictures here. Going back, the greater the order, the greater the strength. But we can also see that the greater the order, the shorter the bond. The distance is going to be smaller. So this is something we should keep in mind from now on. Multiple bonds could be analyzed, and we might have to remember that multiple bonds tend to be shorter and stronger. And the whole reason is that when we have a greater number of bonds, there are more electrons there. So the attraction, keep in mind that what we have here is an increase in the attraction between the bonded nuclei and the shared electrons we have in that bond. We also need to have in mind the concept of what is a coordinate bond here. Okay, a coordinate bond will be a bond that results from electrons that are being shared that come only from one of the atoms that are just being bonded there. This is something that occurs in different situations. You might see these when some molecules are being formed, when some ions are being formed, or even in the formation of complex ions. Here we can see just 3 different cases. As you can see, here on the ammonium, we can just see that the whole Lewis structure will have one electron pair there with two electrons being shared from the nitrogen. That's what we call a coordinate or dative bond. The same is occurring here with sulfur dioxide. Here, the bond is just taking place with two electrons that are just being shared from the sulfur. And if we just think about the formation of a complex ion, keeping in mind the case of Cooper just with waters, we will see that here the lone electrons in oxygen are getting this Cooper ion stable. But that's also a coordinate bond because these lone pairs are just being shared from the water itself. So it's oxygen just placing the electrons there. So again, just keep in mind that coordinate or dative bonds are just produced when there's only one of those atoms providing electrons in that bond. We will get started now with something really huge. That is the valence shell electron pair repulsion theory. This is a theory that states that the shape of a molecule or ion will depend on the electron repulsion. We must keep in mind that there will be a concept here that will be the concept of electron domain that will be very important for us. An electron domain will be just a region of the space with a high electron density. And so we will consider the number of electron domains from now on to deduce the geometry. Every bond, either if it's single, double, or triple, and every lone pair around the central atom will be considered an electron domain. And so we will consider the electron domains to figure out the shape, as I told you before. The assumptions of this theory are, first of all, electron domains repel each other. Electrons and electrons both have negative charges, so they tend to be as far away as possible from one another. So that's the main principle behind the theory. Electrons just go away from each other. If we have two groups of electron domains, you can see them in purple here. The arrangement is that the two electron domains will just tend to be as far away as possible from one another in an angle of 180. Now, if you have three electron domains around the central atom, the arrangement that will be adopted will be a trigonal planar structure. Angles will be angles of 120 around the central atom. And if there are four electron domains, the arrangement is harder because it's kind of a three-dimensional arrangement so as to minimize the repulsion. This presents an angle of 109, as you can just see here on the right-hand side of the board. These three arrangements do have specific names. The first one is going to be known as linear, the second one, trigonal planar, and the third one is known as tetrahedral. So, having in mind the number of electron domains we have around the central atom, we will be able to identify how these electron domains do separate from one another. We should also keep in mind that non-bonding electrons around the central atom tend to exert greater repulsion. And that means that they are not just localized within the bond, they tend to be just there. And so they just occupy, we can just think about them occupying a greater space. This is something that will produce a distortion. We will see that later on. But we should keep in mind that non-bonding electron pairs will exert a greater repulsion compared to bonding pairs. The other thing we should have in mind, even though we mentioned that on top, is that multiple bonds will always be considered as one electron domain. Even though you might have a double bond or a triple bond, do not think about those ones as many electron domains. All the electrons there will be all together, and those will be considered as a single electron domain. The procedure to apply the theory is quite simple, but the key step, as I already explained you before, is to draw the Lewis structure correctly. First of all, we should draw the Lewis structure. That's the first step. Once we're done, we should count the number of electron domains we have around the central atom so as to figure out something known as the electron geometry. The electron geometry is related with the number of electron domains around. So far, the electron geometries we might see are these ones. With higher level students, we will later on see additional ones. But at this level, we will get started with these three electron geometries: linear, trigonal, planar, and tetrahedral. We need to determine here, out of those electron domains, how many of those will correspond to bonding electron domains and how many of those will correspond to non-bondings, so as to deduce the geometry. Because the thing is, one thing is just take into account the electron domain geometry or the electron geometry, and another thing is to deduce what we call the molecular geometry. The molecular geometry will take into account if there are lone pairs there, and the thing is, if there are lone pairs, the electronic geometry will differ from that we will call the molecular geometry. Just to see an example, let's take one that is very easy. Most of you have seen this before. This is the Lewis structure of water. We can just see here that the oxygen has 2 bonding pairs and 2 lone pairs. If we think about the number of electron domains here, there are 4. We have 2 bonding and 2 non-bonding pairs. But as there are 4 electron domains, the kind of arrangement in terms of electronic geometry will be tetrahedral. We can see this here. The angles there should be near 109.5. But the thing is, we have 2 lone pairs there. So even though this is the electronic geometry, it's not the actual shape of the molecule. The molecule will have this kind of V shape we can see there. So if we take into account that some of them are lone pairs, we can just think about the real shape, just considering the shape of the molecule with the real ones we have there. The kind of shape we have here can be called bent or V-shaped. So here we can see the difference between what we call electronic geometry and molecular geometry. And just a tip for the exam, keep in mind, you might be asked for both. So be very careful when you have a question and just pay attention just to identify clearly the type of geometry being asked, okay? As you can see on the arrangement I did for water there, you can see that sometimes this kind of representation might appear. We might use wedged and dashed lines so as to represent some bonds that are not within the plane of the screen or within the plane of the page. That's like a methodology we will use so as to represent these 3-dimensional bonds, so as to represent the kind of shape we will have. It's pretty hard to do it. The thing is, we just use this technique to represent some bonds with wedges so as to show the bonds that are coming out of the plane, and dashed lines so as to show bonds that are going into the plane just behind your screen. Let's just continue. For the ones that are asking if the presentation will be shared later, you can see on the chat a link to the presentation. Keep in mind that the presentation has been shared there, so everything I'm just sharing here with you is just there. So don't be worried. If there's any specific question about what we are just discussing here, feel free to add a question on the question and answer section. We will go over that later, okay? Let's go now to molecular geometries. We just discussed that water has an electronic geometry that is tetrahedral, but its molecular geometry was bent or V-shaped. So what is meant by a molecular geometry is the actual shape of a molecule. We have to keep in mind that non-bonding pairs will exert greater repulsion and will occupy more space. So we must keep in mind that distortions might take place. I mean, distortions in terms of the angles we may have. Here on the board, I just stated 4 examples so that you can just see the kind of arrangement. All of them, I mean, all these 3 molecules have 4 electron domains, but the difference is just the number of lone pairs you have, the number of non-bonding pairs. In the case of methane on the left, all the electron domains do correspond to bonding pairs, so the angle there is exactly 109.5. But if you just go to the ammonia, there is 1 lone pair. This lone pair we have here exerts some kind of repulsion. And that means that the angles here will not be exactly 109.5. They are just going to be slightly distorted. The same occurs with water. The presence of 2 non-bonding pairs is just going to produce some kind of distortion in the angles. And the angle here is just going to be smaller. I would say even smaller than ammonia compared to 109.5. This is something we should have in mind in terms of identifying the angles. Keep in mind that in IB exams, you might be asked to estimate angles. So if there are lone pairs, always keep in mind that angles could be slightly smaller. In this specific case, the angles here are 109.5 for the methane, 107 for the ammonia, and 105 approximately for the case of water. So as you can see, the distortion is clear. You are not expected to remember these numbers by heart. Don't be worried. Keep in mind that you might be asked to estimate something. So if you're asked to estimate, let's say the angle of water, and you just estimate 106, 107, or 103, it will be fine. Of course, the whole purpose of estimating is just saying that the angle will be slightly smaller than 109.5. This is a summary of the different situations we may have, the number of bonding and non-bonding domains we might have, and the corresponding electronic and molecular geometries. You can just keep it to study, but keep in mind that the purpose is not just remembering all this by heart. I mean, you're not expected to remember all this by heart. It's just about thinking about the structure, drawing the Lewis structure, identifying the electron domains, and just trying to deduce what you have there. Do not forget, because this is a very usual error, multiple bonds will always count as one electron domain. Let's now move forward with bond polarity. We must keep in mind that when we have a structure, a covalent structure, electrons are shared, but the electrons might not be evenly distributed. You might have a partial charge over a bond, because sometimes the electronegativity is just different. If we just compare the electronegativity of hydrogen and chlorine here, we can see that chlorine is more electronegative. And so chlorine will have a greater tendency to attract the bonding pairs of electrons. You can just see here that I just did over the chlorine a partial negative charge, because most of the electrons will tend to be closer to the chlorine. So we will say that there's an electron deficiency over the hydrogen and an excess of electrons over the chlorine. That is represented as shown here with the partial positive and the partial negative charge. In non-polar molecules, there's an even distribution, such as here. If the electronegativity is exactly the same, electrons will be equally shared. But we should keep in mind that if the electronegativity is not the same, electrons will not be evenly distributed. The uneven distribution of electrons causes what we call a dipole moment, meaning that there will be electrons closer to one side of the molecule, and so a polarity will appear. The concept of polarity is just that one side has a greater electron density. In a molecule, the polarity should be considered taking into account the bond polarity, but it's not enough just to consider the bond polarity. We should also keep in mind the distribution of electrons throughout the whole molecule, and it's going to be more complex. Dipole moments will be measured in device, but keep in mind you won't be asked to calculate the dipole moment. All you will have to do is to identify if a molecule is polar or not, and you might be asked to compare. The molecular polarity, again, relies on the polarity we might have on a bond, but it will also depend on the geometry. Let's just see this case. Here, in the case of water, we have some bond polarity here. I mean, oxygen is more electronegative than hydrogen, so there's some bond polarity here and here. And as a result of those two bond polarities and the result of the shape of this molecule, the molecule turns out to be polar. Now, if we think about carbon dioxide, this molecule results as a nonpolar molecule, because even though the molecule will have polar bonds, these polar bonds do present a polarity that is exactly the same and with opposite direction. So the bond polarities here are just canceled. And as a result, the molecule results as a non-polar molecule. Finally, if we just think about a more complex molecule such as tetrachloromethane, is the same. I mean, here, the 4 bonds we have exactly the same magnitude for the polarity. And even though it will be harder just to see this, because it's harder to see that visually, the thing is the polarities here will get canceled. It's the same as in carbon dioxide, except that it's easier just to see that polarities are getting canceled in carbon dioxide. If you have 3 or 4 bonds and all of them have exactly the same polarity, the thing is those polarities are just being canceled. Let's just move forward with the next part. We should keep in mind in terms of molecular polarity that if polar bonds do not cancel out, the molecule will result as a polar molecule. But if bond dipoles do cancel out, such as the cases we saw for carbon dioxide and tetrachloromethane, molecules are nonpolar. We should be really careful while comparing. Check out here the case of tetrachloromethane and trichloromethane. The diagram allows us to see here what we have. In the first case, the magnitude of the bond polarity is exactly the same for the 4 bonds we have. Even though it might not be that easy, the magnitude is just the same. But if we just take the second case, the magnitude for the polarity is not the same for the 3 bonds. We have 3 bonds there, but the difference between carbon and hydrogen is not that huge. I mean, carbon is slightly more electronegative than hydrogen, but the difference here is tiny. I'm just going to make a tiny arrow there. So you don't really have to analyze it in detail, but you must understand that the molecule we have on the right-hand side here does not present bond dipoles that are just being canceled. You have bond dipoles that are just producing a resultant dipole over the whole molecule. Let's go now to another kind of structures that you should know. There are some structures known as giant covalent networks. These are one specific type. Sometimes covalent bonds will not produce molecules, so we should have in mind that we don't always have molecules as a result of sharing electrons. So if we don't really have molecules, we might have these giant covalent networks. The whole thing is that here, atoms will be bonded as part of a huge structure. And there are some specific structures you need to remember. The whole thing is that they produce a very huge three-dimensional structures. Sometimes it might be bidimensional. We will see one of those cases now. But the thing is, those arrangements are arrangements you need to remember. There are some cases you just need to remember. First of all, you should be aware about the carbon allotropes. I have not stated all the allotropes here, but there are a few. We can see the structure of diamond, graphite, and graphene. Diamond presents every carbon strongly held by 4 covalent bonds. Every carbon there is tetrahedral, and every carbon will be part of a huge structure. Now, if you just compare it with the structure of graphite, check out that in graphite, every carbon has only 3 bonds, not 4. Every carbon will have 3 covalent bonds, and then there's going to be a van der Waals attraction between the carbons of one layer and the next one. We basically have like sheets of hexagons that can slide over each other. So this is kind of a huge arrangement, but it's completely different if we just think in terms of the arrangement for every carbon, okay? Tetrahedral structures or tetrahedral arrangements for diamond, but in the case of graphite, every carbon will have kind of an arrangement in a trigonal planar geometry. In the case of graphene, you can just think about graphene as a 2-dimensional structure. It's just one layer, and it's similar to graphite, but you just have one layer where carbons are strongly held by 3 covalent bonds only. Now, again, I don't really think you might be asked to draw. You should have these structures in mind so as to compare them in case you're asked to do so. For higher level students, you might have to know the hybridizations. We'll talk later about it. But the thing is, you need to have in mind these structures. We also need to have in mind the silicon structure and the silicon dioxide structure. Silicon is very similar to the structure of to the structure of diamond. Every carbon in silicon is strongly held by 4 covalent bonds with other silicons, and in the case of silicon dioxide, it's different. Every silicon will have a connection in a tetrahedral arrangement with 4 oxygens, and then every oxygen will have a connectivity with 2 silicons. So the arrangement again will be kind of a 3-dimensional structure, but this 1-to-2 ratio between silicon and oxygen. The drawings here are just included for the purpose of having them in mind. Keep in mind, you will have to recall these structures and you might be asked specifically to give details about those. We will now make reference to the intermolecular forces. Molecules do have shared electrons within their structures, but molecules can interact with one another through attractions. Intermolecular forces will make reference to these attractions between molecules. It's an attraction between molecules. It's something that takes place between the molecules. And intermolecular forces will be really important in condensed states, meaning in the liquid or in the solid state. In the gaseous state, intermolecular forces tend to be really small because particles are far away from one another. Now, these attractions will depend on the size and the polarity of the molecules. We will see the different types of intermolecular forces in detail. We can see that there are different types that do exist. The most usual one are the London dispersion forces, dipole-induced dipole forces or dipole-dipole, and hydrogen bonds. The first 3 are classified within a term that includes them all, that is the van der Waals forces. Let's go with them. The London dispersion forces is the first type, and is a type of attraction that is always there. It's produced just because electrons within a molecule can't just undergo distortions, and the electron cloud can just produce a random movement so that electrons can suddenly get closer to one side of the molecule. This temporary distortion will produce a polarity, and molecules will start getting attracted to one another due to these temporary polarities. We should have in mind that the greater the size of the molecule, the greater the London dispersion forces. This is something huge. And if we are comparing molecules of the same size, we should keep in mind that molecules with the same size might differ in the London dispersion forces due to their shape. Just to give you an example, both molecules here, both of them have the same molecular formula. Both of them are carbon 5, hydrogen 12. These 2 are isomers. But if you just think about the arrangement they have, the one on the left is kind of a straight chain, but the one on the right is not a straight chain. You have many branches there, many side chains. The interaction of the molecules is not the same. I mean, pentane can just interact through all this space here. But if you just think about the second one, the interaction is not as easy as on the first one. So the London dispersion forces on the second one tend to be weaker. And so, for example, it's easier just to melt them. Having said all that, we can just make reference now to another type of force, dipole-induced dipole forces. Sometimes molecules that are polar can induce a dipole over the neighboring molecules, even though they might be non-polar. Just think about the polar molecules such as hydrogen chloride. Chlorine has a very huge partial negative charge because it's more electronegative than hydrogen. If you have a molecule next to itself that is non-polar, a dipole might be induced there. Keep in mind that the chlorine here will have a huge partial negative charge, and so electrons in the hydrogen might go far away from the chlorine. This is an induced dipole. This type of interaction is just one type, but we might also have dipole-dipole forces of interaction with polar molecules. If polar molecules do interact with neighboring molecules, the permanent polarity they have might produce an attraction. The attraction will occur between the partial negative side of one molecule and the partial positive side of the other one. The strength of these will depend specifically on those partial charges. Finally, there's a third type of attraction known as hydrogen bonds. There's something huge about it. Don't think about this type of attraction as a real bond, because as hydrogen bonds are called bonds, many students will get confused here and they will just think that hydrogen bonds are actual bonds. That's incorrect. Hydrogen bonds are attractions that do appear when you have a highly electronegative atom, and this highly electronegative atom causes an attraction to an hydrogen bonded either to fluorine, nitrogen, or oxygen. But again, keep in mind that the hydrogen bond itself, it's not a real bond. You can just see the dashed line here. The hydrogen bond is an attraction between one hydrogen and a highly electronegative atom from another molecule. Could be the same molecule or just another type, but many students, to be honest, will think that the hydrogen bond is this bond here. That's a huge misconception. Don't think about it, because that will be wrong. The hydrogen bond, again, will just make reference to the attraction between molecules. It's not a real covalent bond. As I have just been mentioning, hydrogen bonds can take place between molecules of the same type, but also with molecules that are just different. Here we can just see some examples. We can just see water molecules interacting with other water molecules, and the hydrogen from one molecule might be attracted to the oxygen from the other one. But we might also have interactions between different molecules, such as the second case we have here, that is the case of ammonia and water. If we just think about the ammonia and water, the hydrogen from the water might be attracted by the nitrogen in ammonia, but at the same time, the hydrogens from the ammonia might also be attracted from the oxygen in water. So there are like two different types of hydrogen bonds we might have here. And finally, on the right-hand side, we can see a type of hydrogen bond that has something special. Here, the hydrogen in water might be attracted by the oxygen in dimethyl ether. Now here, keep in mind that this molecule you have here cannot just produce hydrogen bonds on their own. I mean, if you just have this ether alone, there will be no hydrogen bonds there. But if you have the ether in water, you can actually have hydrogen bonds, because you have the OH bond here, and then the hydrogen bond will be just produced because the other molecule has a highly electronegative atom, such as the oxygen there. So again, it's very important to identify hydrogen bonds and remember the conditions required for that one. As a summary, we can just say that London dispersion forces will be present in all the molecules. Dipole-induced dipole or dipole-dipole forces will take place depending on the type. Remember that dipole-dipole forces do require to have polar molecules. And finally, hydrogen bonds do need the presence of some specific bonds within the molecules, such as FH, OH, or NH bonds. These intermolecular forces do not have the same strength. In general terms, we can just say that London dispersion forces tend to be weaker than dipole-dipole forces, and those tend to be weaker than hydrogen bonds. But keep in mind that this is something that allows us to compare molecules that have a similar size. If the size is completely different, well, London dispersion forces can be huge. In general terms, in IB exams, you're always asked to compare molecules with a similar size, so don't be worried about that. Let's now go over the concept of the bonding triangle. You might have heard about it, and I would like to go over the details. The bonding triangle allows us to identify the position of a substance within a triangle that has these three sections. One corner will correspond to metallic structures, the other one to ionic, and the other one to purely covalent structures. The triangle is not as easy as this one. You have the triangle in section 17 of the chemistry data booklet, and the triangle is likely to be like the one I stated here on the right. On one hand, we have to work out the electronegativity difference for the substance we have, and on the other hand, we have to deduce the average electronegativity. The whole purpose is to calculate these two for a given substance so as to locate a substance within the triangle. Once we're able to locate the substance there, we will be able to predict properties. As you know, ionic structures do not have the same properties as metallic ones and do not have the same properties as covalent structures. So it's very helpful in terms of predicting. But the whole purpose of using this one is also to have in mind that there is no substance that is just classified as 100% ionic. Most substances will be classified, let's say, as ionic, but might have a small covalent character as well. As you can see on the right-hand side here, there's kind of a percentage of covalent and percentage of ionic, meaning that there's always kind of a continuum here. We should have in mind that it's wrong just to think that something is classified as ionic, and the model that allows to explain all the properties there will be 100% the ionic model. Sometimes these two models coexist, and we will see that in detail. We always need to locate, as I said before, we need to locate in the triangular bonding diagram a substance. And to do so, we should have in mind that sometimes it's easy to identify that some substances might be here, some other ones might be here, and some other ones might be here. But we should have in mind that there might be substances that might be on the edge, such as here or here. So for those ones, we will say that it's hard to classify them. I mean, the use of the bonding triangle will not be perfect. And sometimes we might find substances that will have properties of different types, and different models might allow us to explain them. The case of magnesium diboride is one case that will help a lot. If you just think about the electronegativity of magnesium and the electronegativity of boron, you can just calculate the electronegativity difference and the average electronegativity here. Now, if you just take the bonding triangle, you can just try to locate it here. Now, the average electronegativity is near 1.65, so will be something here. And the one that is the electronegativity difference is 0.7. So what is meant by that? It will be something there. It's not that easy, but you will have some time in the exam, you will have a ruler, and you will be able to do it. What is the thing about it? It's not that easy to say the type of properties we'll have for this one. So don't think that the bonding triangle is just perfect. In IB exams, you might be asked about the properties of some substances, but you might also be asked about the limitations of the use of this model, okay? If you have something on the edge, one type of bonding might not be enough, okay? It might be difficult just to think about it as one type of bond, so you might talk about the percentage character, meaning the character you have on the left-hand side. You might pay reference to the presence of both ionic and covalent character here. Let's get started with some questions. So far, we have been reviewing a lot about the theory. I can see there are some questions and answers, so we will go later on over those ones, but let's get started with some practice questions. Keep in mind that there are many practice questions on the Revision Village website. We will go with some of those together, and the whole purpose is to get you trained for the exams. Here we have a question where we are asked about the oxygen-to-oxygen bond. It says, which shows the oxygen-to-oxygen bond in order of increasing average bond enthalpy. If you remember, we discussed that the bond order and the presence of multiple bonds will allow to see a greater strength. So we should expect the average bond enthalpy to be greater for the triple bond and smaller for the single. So out of the options we have here, the third one is the correct one, because there we have the single bond as the weakest, meaning the lower average bond enthalpy, less energy will be required to break that one, then the double one, and then the triple bond there. Let's try the next one. Check out this one. I just want you to think, to work this out, you must have in mind the structures of these three allotropes. Otherwise, it will be really hard to work it out. So here, it's very useful to have in mind the diagrams I shared with you previously. If you just have to think about the type of arrangement we have here, keep in mind that graphene can be described as a layer, but it's a layer that is not necessarily in 3 dimensions. It's correct, I would say it's correct to think that it's a bidimensional material. And the angles there, keep in mind we discussed that every carbon there has a trigonal planar structure, so angles there will be 120. For diamond, we can think about diamond as a structure with every carbon bonded to other 4 carbons. And the angles there will correspond to an arrangement that is tetrahedral, meaning we can just say that the angle there is 109.5. Finally, for graphite, we have these hexagonal layers, such as in the case of graphene, but we have layers over one another, weakly attracted to one another that can slide over each other. Finally, the correct answer here will be the description stated in C. Again, I would like to highlight, just having in mind that exams are coming soon, that you should have in mind these structures. You're not expected to sketch them in an exam, even though it could be asked to provide the sketch. I don't really think that's that usual, but you should have in mind the arrangements so as to provide details about it. I can see some students suggested that the answer was B. Take into account that in B, what we have there is that it says that the graphite is 2-dimensional material. But in graphene, if you just look at it, you have layers over one another. So it's kind of a 3-dimensional arrangement, to be honest. Okay, let's just move forward with another one. Here we have a molecule and we are asked about the bonds. To think about it, we have to think about the electron domains. For the first carbon, we have 1, 2, 3, 4 bonds, meaning this is a carbon with a tetrahedral arrangement. So I would expect around that one, an angle of 109.5. The second carbon here presents 1, 2, 3 electron domains. This one will be trigonal planar, and so I would expect an angle here of 120. And for the nitrogen, you might think we have 3. I mean, we have 1, 2, 3, but the lone pair will also count. So nitrogen here has 4 electron domains. Out of those 4, we have to think there's 1 non-bonding pair and 3 that are bonding. So what is the thing about it? I would expect an angle of 109.5, but as we have 1 non-bonding pair, I don't really expect the angle to be exactly that one. I would expect it to be slightly distorted. So I would say that it will be smaller than 109.5. So if we just check it, the correct one here would be option D. Check out that here we need to recall the idea that lone pairs exert a greater repulsion. So in the case of the nitrogen, we should have in mind that the lone pair there on top will exert a greater repulsion, and so the angles will be slightly smaller. They will be distorted. Okay, here the question says, which statement about aluminum nitrate is correct? First of all, we need to understand what is aluminum nitrate. The structure of aluminum nitrate will be made with aluminum and nitrogen. Okay, aluminum is from group 13, nitrogen from 15. So these two combine like this. We have to consider all these descriptions, but the thing is, we need to have in mind that we might have to use the bonding triangle to work this out. Okay, so what is the thing? You need to locate this structure in the bonding triangle. You need to work out the electronegativity difference and the average electronegativity here. And after doing so, we just need to locate it. Of course, you will have the chemistry data booklet in your exam. If you just locate it, you can just see that it's there on the edge. And so, as it's there on the edge, we can just say that the correct answer will be C, because it will present some properties that will allow it to be classified as covalent, but some other ionic characteristics here. Keep in mind that it's not always about being on the ionic side, the covalent side, or the metallic. Sometimes you might have questions where you will be exactly on the edge. Let's try now a harder question, a paper 2 style question. This is a typical question where you're asked about a molecule. In the first part, we are asked about ammonia and its structure. We should get started with the Lewis structure, so I will state nitrogen as the central atom and 3 hydrogens as peripheral atoms. And as we discussed before, it's all about getting started by stating 1 bond shared between each. And so I will state the electrons there. And then, just to complete it, I will state the lone pair over the nitrogen. The second question says that we need to explain why covalent bonds in ammonia are polar. Here, the whole thing is that we need to think about the electronegativity values. The electronegativity of hydrogen is just 2.2, but that of nitrogen is 3, meaning that nitrogen has a greater ability to attract bonding pairs of electrons. And so electrons tend to be closer to the nitrogen. That's the whole reason behind the polar bonds. Now, if we have to answer the third one, it says to say the molecular geometry, we need to think about the electron domains. Keep in mind that here, around the nitrogen, we have 4 electron domains. 3 of those will be bonding and 1 will be non-bonding. If we just identify that, the kind of arrangement will be classified as trigonal pyramidal. We can just think about nitrogen as a molecule, as part of a molecule that has a lone pair on top. And if you just think about those bonds, you can just try to draw them like this. Just trying to make the diagram so you can see. So this is kind of a pyramidal structure. Okay, so trigonal pyramidal is the kind of arrangement you should suggest. For the next one, you're asked to explain why the bond angle of ammonia differs from that of ammonium. Here, you just have to think, how is the structure? What is the structure of ammonium? So we can just say, okay, here the angle is probably smaller than 109.5. We already know that we have a lone pair over the nitrogen and that lone pair exerts greater repulsion. But what about ammonium? First of all, ammonium is an ion. We have nitrogen in the middle, but there are 4 hydrogens there. If we just include the electrons, we will see this kind of arrangement. Do not forget that in the case of an ion, we need to include the brackets and the charge on top. Here we have 4 electron domains, but all of them are bonding pairs. So the molecular geometry is tetrahedral and the angle will be exactly 109.5. The whole difference is that the angle in ammonium is 109.5, but in the case of ammonia, it must be smaller just because we have a lone pair of electrons exerting repulsion there. Remember, lone pairs of electrons do exert a lot of repulsion. Let's go now to the next one. Keep in mind that in this case, you're not expected to remember that ammonia is 107 in terms of the angle. You're just expected to suggest an angle smaller than 109. The next part presents this kind of graph where we can see the tendency for the boiling points. We are asked to explain the variation of the boiling points in the graph using section 8 of the booklet. On section 8, you have all the electronegativities, so you can just think about those ones. The first thing I would like to highlight is that the case of ammonia is kind of an exception here. Its boiling point is greater than expected, and the thing is that that would correspond to the presence of hydrogen bonds in ammonia. Out of the molecules we have here, ammonia is the only one that can present hydrogen bond interactions between ammonia molecules with other ammonia molecules. The other ones will not present hydrogen bonds. So this is a huge difference. By the way, for the other ones, we can just see this increasing trend here, and that's probably related with the size. Now, identifying the presence of hydrogen bonds in ammonia is definitely something important here, But at the same time, we should also make reference to the fact that as you go down the group, I mean, all these molecules do have a central atom with 3 hydrogens, but all of them are just part of the same group. So as you go down the group, the electronegativity of those elements is just decreasing. Keep in mind that even though the electronegativity might decrease, the size of the central atom is increasing, and so more electrons are involved there. As a result, we have more London dispersion force. I mean, there are more intermolecular forces, and so we have this increasing trend. Even though ammonia is just an exception, we have this increasing trend because the attractions are getting stronger. So always make reference to the fact that the size will matter, but keep in mind that if there's any kind of exception, such as the case of ammonia, we might have to make reference to the presence of hydrogen bonds there. Okay, we have just finished the standard level section. Okay, so it's time for some questions and answers before saying goodbye to the standard level students. So I will just go over the questions. Let me just see the questions so as to answer some of them. To decide in a Lewis structure, to decide which one is the central atom, you need to check which one is not repeated. In the case of ammonia, you have 1 nitrogen, 3 hydrogens, so you just consider the one that is not repeated as the one that will be in the middle. It's always the same. If there are more than 2, well, in general terms, I will say that if you have organic molecules, sometimes organic molecules are quite challenging for Lewis structures. The usual thing is that carbon tends to be in the middle. Carbon tends to be the central atom. So if you have a Lewis structure with carbon, you can just put the carbon in the middle and then arrange everything around it. There's a question about coordinate bonds that say, why do coordinate bonds happen? And if that's affecting the stability, keep in mind that coordinate bonds do happen when you have electrons that do form an attraction that both electrons come from the same species. In the case of complex ions, the coordinate bonds tend to produce stability, but the thing is, you just need to identify it in the case you have. I mean, if you're asked to identify the coordinate bond, all you have to do is to represent them and just see the one that is just formed from a pair that comes from the same molecule. Okay, I can see that someone is asking about the polarity I just showed in device for trichloromethane. You don't really have to calculate that. I just stated that as an example. You will never be asked about the bond, not the bond polarity, the molecular polarity. Don't think that the polarities might be asked. You will never be asked to calculate it, but you might be given the polarity and you might be asked, okay, why this molecule is polar, whereas this other one is not. You might have to compare, but you will never be asked to calculate it. I see here someone make reference to the three-dimensional structures on my slides, the reference in the carbon allotropes. Keep in mind, it's true I made reference to the three-dimensional arrangements, but in the case of the graphene, we call it bidimensional because if you just check, it's a layer of hexagons. So even though it's three-dimensional, it's just one layer. And so you can also make reference to that one as a bidimensional structure. It's something you should have in mind. So yeah, it's a slight difference. It's not incorrect because all the allotropes will be included within this three-dimensional structure, but that one, specifically the graphene, can be considered bidimensional. You might have to remember other allotropes such as the fullerenes. Yes, someone is asking about it. Nanotubes, you might have those ideas in mind. I have not included them here just for time purposes. I mean, there are many, but you won't be expected, of course, to recall them in detail. The whole thing is just having the idea about how those ones will look like in case you're asked to compare. Okay, someone stated that the polarity is related with a molecule being symmetrical or not. So yeah, that's correct. But keep in mind that when we're making reference to symmetrical, I mean, it should be completely symmetrical. Tetrachloromethane, meaning carbon with 4 chlorines, it's kind of a symmetrical molecule. But if you just change 1, 2, or 3 of those chlorines by something else, it will not be symmetrical anymore. Many questions about the polarity. Again, you don't really have to state the polarity calculation, so don't be worried about it. And in terms of the bonding triangle, someone is asking about the limitation. The limitation is that sometimes some substances might be on the edge, so you might have to classify them or just provide the characteristics of those ones, considering that they might have a percentage of covalent character and a percentage of ionic character. For silicon dioxide, we will say that silicon dioxide, it's a three-dimensional arrangement. Someone asked about it, so keep in mind it's three-dimensional. And, well, yeah, you need to know the fluorines, as I said before, and well, many questions about the calculation of the device that I already answered. Okay, I was just answering questions from the question and answer section. So now you can keep on stating questions there. We are just going to continue now. I will thank you all the standard level students for joining. We would love to receive your feedback, and keep in mind that all the study sessions are designed for you. They are supposed to help you getting ready for your exams. So please use the QR code you have here just to provide feedback. It will be great to hear from you. If you just think that it will be great to have a study session about another topic, let us know which topic will be good for you. And don't forget that on the website, you have prediction exams, you have past paper solution videos with many explanations that will help you a lot. So just feel free to go there and use all the information on the website. And remember, there's the Revision Village app. You can just use it to follow all the information there. And now it's time to continue with the higher level content. Keep in mind, you can just continue stating questions on the question and answer section. We will go over those ones at the end, as we just did right now. Okay, let's move forward. For high-level students, there's a concept that is the concept of resonance that you should have in mind. Some structures might present more than one resonance structures. More than one Lewis structure. And so the whole idea behind this is that when you have different possibilities, you have one molecule or one ion that might be represented with different structures, we always make reference to the fact that the structure is not just described with one of those diagrams we did. The structure can be described as a mixture of all those ones. The structure can be described as an hybrid of those ones. So the concept of resonance structures makes reference to the fact that sometimes when bonds might change their position, we might have different possibilities and the real structure will be kind of a mixture. For the carbonate ion, that is the previous one we saw at the beginning, I just showed you before that there's a double bond within the structure. Now, check out here that the double bond could be anywhere. I mean, we have 3 different carbon to oxygen bonds, and the double bond could be in any of those 3. So for the carbonate ion, we wouldn't say there's one structure. We'll say that there are 3 resonance structures that do represent the ion itself. What is the evidence about this one? Why can't we just say that the double bond could be anywhere? Well, the thing is that if you just check the carbon to oxygen bond length and bond strength, you won't find that they're single bonds and double bonds. All the bonds within this ion have the same length and the same strength. So that's an evidence of the delocalization of the electrons throughout the structure. The 3 bonds have the same length and strength, and so electrons are just said to be moving around. In many books, you will see the term resonance hybrid. This is used just to make reference to the fact that the 3 structures are like mixed together, producing the structure of carbonate. And in many books, you will also see this kind of a representation. Rather than stating 1 double bond and 2 single bonds, you might see 3 bonds that are kind of an intermediate between single and double. Okay. In a live exam, you're expected to show like the 3 structures and just making arrows between those. Do not forget, if you have an ion, you need to include brackets and charges on top. Let's talk now about the expanded octets. Expanded octets is a concept that applies because some atoms might exceed the octet rule. They might have more than 8 electrons around. And this is known as the expanded octet. They might have 10 or even 12 electrons around. As a result, we might have geometries that won't be just linear, trigonal, planar, or tetrahedral. More geometries will appear. We might have 5 electron domains or 6, and so there are many other possibilities. Here we have a summary you can just add to the previous one. Now let's go into the detail, because one thing is the electronic geometry and another thing is the molecular geometry. Depending on the number of groups we have, I mean, if we have 5 groups, 5 electron domains, the electronic geometry will be trigonal, bipyramidal, but we might have lone pairs. If we have lone pairs, geometries might be seesaw or T-shape. Everything depends on the number of lone pairs. I mean, seesaw will appear if we have a lone pair here. T-shape will appear if we have 2 lone pairs here. I'm just making dots there. And if we have 6 electron domains, the kind of arrangement will be tetrahedral, as you can see here below. And if you have 1 lone pair, the lone pair will remain their actual, so it will be square pyramidal. And if you have 2 lone pairs, will be on top, another one will be below, and so square planar will be the molecular geometry. These are just shapes you need to learn. I just made these drawings to make it easier, but of course, it's just about drawing Lewis structures first, identifying the electron domains around the central atom, and then just moving forward. In the representations I did there, you will see the use of wedge lines and dashes as we discussed before. Keep in mind that I'm using the wedged and dashed lines just to show the equatorial bonds, meaning those in the plane, and then there's always one on top, one below, so as to show the actual ones. This is just something I do for representation purposes. This is the summary for higher level students. Here you have everything we saw for standard level, and then we are adding here the different types we have for high level. Okay, keep in mind, you're not expected just to remember them by heart. You are expected to be able to draw Lewis structures, identify the electron domains, identify the electronic geometry, and then by distinguishing between non-bonding pairs and bonding pairs, you should figure out the molecular geometry. Let's go over another important concept we should have in mind, that it's the concept of formal charges. When we have a Lewis structure, determining formal charges will allow us to identify different charges over the atoms that are just part of the molecule, and that is something that can be really useful. This is kind of a charge. It's not actually a charge. Keep in mind that we have a covalent molecule, so electrons are actually shared. There are no charges here, but the concept of formal charge is like the charge they should have if electrons are lost or gained. So it's like an ideal concept. We can calculate the formal charge over an atom by doing the valence electrons you have there minus the non-bonding electrons minus 1/2 of the shared electrons you have there. This is something useful because over a molecule, you can just calculate the formal charge for each, and that will allow you to compare different Lewis structures. If we compare, we can just deduce formal charges, we can get the sum. We should always check that the sum of the formal charges for a molecule should be the same as 0, because molecules are neutral. And if we have an ion, the sum of all the formal charges should add the charge of the ion. Now, to assign formal charges, we just draw the Lewis structure, we just apply the formula we saw before, and what is the whole purpose? We can use the formal charges just to identify what we call the preferred structure. This is something you might see in exams, either in multiple choice questions or paper style questions. You might be asked to calculate formal charges and suggest the preferred structure. So what are you just going to do? First of all, you will draw the Lewis structure and you will get the formal charges, but then you will just compare. The structure with the formal charges that are closest to 0 tends to be the one preferred. But if you have too many charges, you can also check the difference. The formal charges that are huge do not tend to represent the most stable structure. Usually those ones that tend to be closest to 0 are preferred. And by the way, if you have a negative formal charge assigned to the most electronegative atom, well, that's something preferred as well. So there are many things to have in mind here. Let's see how to identify formal charges in one case. Let's just say we have sulfur dioxide. If I just had to identify the formal charges over each of those, let's get started with this oxygen. I will start by counting the valence electrons. The oxygen here will have 6. Okay, those 6 that are just there are the valence ones. So I will start by adding 6. Then I will subtract the lone electron pairs, not lone electron pairs, the lone electrons, the ones in lone pairs. This one, this one, this one, and this one will be subtracted. So we will subtract 4. And then we will subtract 1/2 of the bonding ones. All the bonding ones are those 4 electrons we have there. So all we have to do is this calculation here. As you can see, for that oxygen, that's the calculation we have. 6 minus 4 minus 4 divided by 2. The formal charge for that oxygen on the left-hand side is just 0. If we just do the same for the sulfur on top, sulfur has 6 valence electrons. So we state 6, then we subtract 2 because we have 2 lone electrons on top. And then if you just check the bonding pairs, we have 4 on the left, 2 on the right. So we should do 6 divided by 2. The formal charge here will be 6 minus 2 minus 6/2 plus 1. Finally, for the oxygen on the right-hand side, there are 6 valence electrons. There are 6 electrons as non-bonding electrons, and then you have 2 electrons shared, meaning we will do 6 minus 6 minus 1/2. That's minus 1. Check out that if we add the formal charges of all these, the overall number is just 0, because sulfur dioxide is neutral, and so formal charges should add 0 for molecules. Being able to apply this kind of calculation, it's very important for you. Keep in mind this might appear in a paper 2 or in a paper 1. Another huge concept is being able to identify sigma pi bonds. Covalent bonds can be formed by the overlap of some orbitals so that electrons can be shared there, but there are 2 types of overlaps we will see. The first type is a direct overlap. We will call that one a sigma bond. And if we have a sideways overlap, we will call that one a pi bond. These have different nature, and we will see some cases right now. In the case of sigma bonds, could be direct overlap of 2 s orbitals, which are spherical. Could also be a direct overlap of an s orbital with a pi orbital, which is just there. Could be 2 of those as well. But all of them, as you can see, do present a direct overlap there. Okay, here we can just see the direct overlap. In the case of a sideways overlap, it's just completely different. We can see here that if we have vertical orbitals, the overlap can occur, but you will not have a completely direct overlap. This is what we call a sideways overlap. What we have here, it's 1 pi bond formation. How do we identify this? If you have multiple choice questions, so questions that are kind of simple where bonds are formed, one strategy is to keep in mind that every time you have a single bond is just a sigma bond. If you have a double bond, we can just say that in every double bond, there's 1 sigma and 1 pi bond. And if there's a triple bond, out of the 3 bonds, we can just say that 1 is produced by a direct overlap, meaning sigma, and 2 of those are just going to be sideways overlap, meaning pi bonds. Let me just show you these with some orbitals in the case of nitrogen. Nitrogen has these pi orbitals. You can just have these 2 nitrogens getting bonded together, so those 2 can get close to one another. We can just see the direct overlap here. It's not that hard to see that. But then we can just think that not only the direct overlap will occur, as we can just see here, the other bonds might produce this sideways overlap, as I explained you before, or the other one. I mean, this one here. So finally, if we just think about the type of interaction we have here, we can make reference to the fact that there are 3 bonds there. Actually, the nitrogen molecule has a triple bond, and that's because you have a direct overlap and then 2 sideways overlaps of orbitals, meaning 1 sigma and 2 pi bonds. Let's talk now about the hybridization. The concept of hybridization makes reference to mixing orbitals together. Sometimes it's easy to think about orbitals, atomic orbitals being mixed so that the new hybrid orbitals will be allowed to produce a new bond formation. In carbon, you can just think about the outermost electrons, the electrons in the energy level 2, as 2 electrons that are originally in an s orbital, and then we have some electrons on pi orbitals. Now, if you just think about it, you can just think that in methane, those electrons will, in atomic orbitals, will be mixed so as to take part into atomic orbitals that are new, that are said to be hybrid orbitals. These orbitals here will be mixed, and from that mixture, we will see a result that is that 4 new orbitals will be produced. When we make reference to these 4 new orbitals, these are produced from mixing the s orbital with the 3 pi orbitals, so we call it sp3. And the thing is that they will produce kind of a tetrahedral arrangement. Now, how would that work? The 4 orbitals will have that kind of shape we can see there, but those will be all arranged around the central atom. So we will have this kind of arrangement you can see here. And that resembles the whole idea of having a tetrahedral arrangement. And so we call this kind of arrangement sp3. Hybridization can sometimes occur not just because the s orbitals will mix with 3 pi orbitals. We might have the s with 2 or the s with 1 pi orbital. Everything depends. So different types of hybridization might be produced. But the whole thing is when we have this mixture, atomic orbitals will produce hybrid orbitals, and the hybrid orbitals will have the same energy. The possibilities we might have are the combination of 1s and 3 pi orbitals for sp3. This will produce a tetrahedral arrangement and a carbon with 4 electron domains around. Another option is to have s with 2 p orbitals there, so it will produce an sp2 orbital hybridization that will produce the carbon with the trigonal planar arrangement and 3 electron domains, and the other one is the sp. That happens if the carbon has 2 electron domains around. Keep in mind that even though I just explained it for carbon, you don't really have to think that this is only applying to carbon. It might apply for other atoms. And all you have to do is to think about the electron domains you have, and you can just associate the number of electron domains you have to the hybridization. 2 electron domains, you can just think about sp hybridization. 3 electron domains, sp2. 4 electron domains, sp3. That's something that will help you a lot. Let's take this case, the case of urea, and let's consider what I just told you about it. If we just try to figure out the hybridization here, we can just think about the carbon we have here, and we can just try to analyze what is happening with the nitrogen here. This carbon we have here presents 3 electron domains around. We have 1, 2, 3. So thinking about that, we can just identify that this carbon will have an sp2 hybridization. Now, if we think about the nitrogen, we have 1, 2, 3, but the lone pair also counts. We have 4 electron domains. The nitrogen here will be assigned as sp3. So identifying the geometries is something very, very helpful so as to figure out the hybridization. Let's get started with some practice questions. Let's think about this one. Here, we can just see the molecule there, and we are asked about the orbitals that are interacting here. First of all, I would like you to see that if we have to think about the interaction here for this carbon, we can just think about the type of hybridization that the carbon will have. Here, this carbon has 3 electron domains around. So the kind of hybridization of this carbon is sp2. So what about that hybridization? The sp2 hybridization in that carbon means that that carbon there will have 3 sp2 orbitals. You can just think about it in these terms. My drawing is not as good as it should be, but that will be the carbon there. And you can just think that then we will have 1 hydrogen here, 1 hydrogen here, and then this one will be interacting with the other carbon, which is exactly in the same situation. Okay. Like I will state the carbons with different color just to make things easier. So the carbon and the carbon. So what about the CH bonds? We can just make reference to the CH bonds, just keeping in mind that we have sp2 orbitals there. Now, what about the carbons being bonded to one another? We do know that carbons do have a direct overlap there. I mean, we can just see the direct overlap. I'm just going to state it in red there. But there's a double bond, meaning that we have a direct overlap, but there's also another type of overlap that is just happening because carbons there have sp2 hybrid orbitals, but there's a p orbital that has not undergo hybridization here. So you can just think that you have also another orbital here, and these orbitals might be interacting sideways. So if we just have to think about it, we can just say that the carbon-to-carbon double bond we have there, one of those bonds is going to be sigma, direct overlap. The other one will be sideways overlap. And so there's a double interaction there. And I would say that we can just make reference to this option here. The answer here is option C. Keep in mind, it's always a good idea to relate hybridization with the whole thing about the geometry and the number of electron domains we have. It's going to be very helpful for you, so take it easy and don't forget to do so while solving these kind of questions. Let's just go to this question. It says, which terms best describes the electron domain geometry here? First things first, we must work out the Lewis structure. Bromine will have 7 valence electrons, and every chlorine will have 7 valence electrons as well. So 7 multiplied by 6 means we have 42, and we can just start stating the electrons around. We will start stating the bromine. We will get started with the bromine with 7 electrons, but we will have in mind that there are 5 chlorines, so we will get started with the 5 chlorines there, and we will start with 1 pair share between each. Then, following the steps I gave you, you're just going to state lone pairs for every chlorine so that every chlorine can achieve the octet rule. By doing so, you can just check that as soon as you state all these electrons, the number here, the overall number is 8 multiplied by 5. So we just have 40 here. But as you can see, there are 2 electrons missing. So what should we do with the extra electrons? We just put them over the bromine. Finally, we can just say that the structure will have around this bromine, oh, let me just remove my drawing. You will have bromine with 5 bonding pairs and 1 lone pair there. If you just think about everything we discussed before, the electronic geometry here is the one corresponding to 6 electron domains, and so it will be octahedral. The correct answer here is D, just because they asked for the electron domain. If you're asked about the molecular geometry or something else, you will have to make reference to a square pyramid here. Let's try a paper 2 question. Here we are given the formate or methanoate ion, and we are asked to answer some questions about it. First of all, we have to determine the number of valence electrons in this one. So all we have to do is to count. The number is 18 because we have 1 in hydrogen, 4 in carbon, 6 in every oxygen, and the negative charge will add 1 there. So overall, 18. We have to draw the Lewis structure. And here, well, many students asked before, what if we have more than 2 atoms involved? Well, as I explained before, when you have more than 2 and you have kind of an organic structure, carbon is usually in the middle. So the strategy is always state carbon in the middle, then the oxygens around, and then you can just fill in with hydrogens. Here, we just can think about the kind of arrangement we will have by stating carbon in the middle, but we are not only asked to draw the Lewis structure for the methanoate ion, we are asked to include resonance structures. So what is the thing? We have to think about the structure, and one of the things that will happen here is that we might have a single and a double bond. But the thing is, the single and the double bond could be in different positions. So it's a must, to gain these 3 marks, it's a must to provide the resonance structures with a variation in the position of the carbon to oxygen double bond. By doing so, you can just state it and it will be fine. I would say that here the square brackets are missing. It's correct to say the negative there over the oxygens. Another option is just to say the negative on the right-hand side of the brackets. Both things are just fine, so just keep this in mind from now on. Okay, let's go to question and answer time. I will go over the questions there just to check. Someone asked about the use of wedged and dashed lines for the representations. Keep in mind that the whole thing is that sometimes some bonds cannot be represented properly. So the thing is you need to have a kind of representation that allows you to show that some bonds might not be within the plane of the screen. So the use of a wedged line, the dark one, will show you that something is getting out of the plane of the screen or is getting out of the plane of your page if you're just checking that structure on a book. And if you have a dashed line, that's showing it's behind the page or behind the screen. So it's kind of a representation that allows you to think in 3 dimensions. It's hard, but it's something you should understand from now on. Okay, someone is asking about, I see a question about polarity as well. Yeah, bond polarities are always related with electronegativity differences, just in case. The thing about the expanded octets is that some elements that are from period 3 and below do have other orbitals, and so they might have this possibility of having what we call expanded octets. Now, it's true that it will not just happen with any cases. We can just consider our phosphorus, sulfur, and why those ones? Because usually the elements that are from period 3 and below will be the ones that will tend to present expanded octets. Yeah, for hybridization, someone asked if the lone pairs should be considered. Yeah, while identifying the hybridization of a very specific atom in a given structure, the lone pairs should be considered because lone pairs will count in order to count the electron domains, and then from that number of electron domains, you will determine the hybridization. Yeah, one pi bond will have 2 dumbbell shapes, and you will have a pi bond with 2 dumbbell shapes, as I did before. I'm just going to do it here. If you have these 2, a pi bond includes this interaction here sideways, and this interaction here. That's 1 pi bond. Yeah. For the question we just did, one of the multiple choice, someone is asking why it's not square pyramidal. The thing is, they ask you for electronic geometry in terms of electron domains. So that's a usual mistake. Many students will just read something about geometry and will think immediately about the molecular. But be careful, because in many questions, you're not asked about molecular. You're only asked about electronic. So there, if you just take the bromine, there were 6 electron domains around, so it should be octahedral. It's not incorrect what you're saying. The molecular geometry was actually square pyramidal, but they ask you for something else. Well, higher level students should learn the cases I gave you for expanded octets, and they should also know about hybridization. This is not expected for standard level students, just in case someone is still here. Standard level students do not need to learn about hybridization, but higher level students do have to learn about it. Now, what do you need to learn? I will say basically you have to learn that if you have an atom with 2 electron domains around, the hybridization is sp. If you have an atom with 3 electron domains around, the hybridization is sp2. And if you have 3 electron domains around, 4, it will be sp3. There are many other hybridizations that do exist. We won't see that. I mean, IV exams will just cover SP, SP2, SP3, but those are not the only ones. Those are the ones covered for higher level students. So be aware about that. And keep in mind, you might also have questions about hybridization when being asked about giant structures like carbon allotropes and all that. So keep in mind, for example, in diamond, the hybridization is sp3, whereas in graphite, the hybridization is sp2. So those are things that could be combined. Tips for paper 1B experiments. Well, that's something completely different, but my suggestion will be try many papers, try to practice a lot, but it's hard. I mean, this is something that could be included in the database questions, but to be honest, it's hard to predict what might be included in database question. Yeah, one pi bond has 2 interactions, one on top, one below, as I did there on the right-hand side. The concept of resonance hybrid is just the same as resonance structures coexisting at the same time. And I think that's it. If I have to describe the electrons in a pi bond, I will just say that those are electrons that are just there being shared from a sideways overlap, and that would be it. Okay, I think I have gone over most of the questions. So the study session is almost over. I would like to thank you all for being part of this session. We would love to receive your feedback, as I said before. It's really important for us to hear from you. Let us know what was useful. If you would like to have another study session about a different topic, let us know. We will design it for you in the upcoming session. And well, if there's any comments, either something we can improve or something you enjoy, let us know. It was really nice to be here. Do not forget that exams are coming soon, so you have on the website many questions so as to keep on practicing from the question bank. You have the prediction exams and you have the video solutions, which is something really good for all of you. So good luck, all of you, and thanks for joining. See you. Bye-bye.